In this video, we're going to look at the derivative function. Start by saying that recall the slope of the tangent to the function f at a point x is given by the following. So the slope of the tangent line of a function of x is given as the limit as h approaches 0 of f at x plus h minus f at x all over h. This can also be expressed as m is equal to the limit as delta x approaches 0 of slope, right, which is the change in y over change in x. But remember that we want the change in x to be infinitesimally small. This is called the derivative of y, or f of x, with respect to x, and can be written as dy over dx, with d instead of the delta, indicating that the differences are infinitely small. We will also see it written as y prime, or f prime at x, which is read as f prime of x. Previously in other videos and in other lessons, we've also talked about like the slope of the tangent as a function of x. Right? And so for that, that is literally called the derivative function. So f prime at x, or y prime, or alternatively dy dx. So there's a variety of different notations that we can use to show the slope of the tangent as a function of x. And so what exactly do we mean by the slope of the tangent as a function of x? Well, let's just take a look at this diagram and see if we can sort of remind ourselves what we're talking about there. So what we can see in this animation is we can see a tangent line moving along a curve f at x, and we can see the slope of the tangent line changes depending on the x value. So we can repeat this by saying the slope of this tangent line is a function of x, because the slope changes depending on the value of x. Slope is your dependent variable and x is your independent variable. Alternatively, you can input a value of x into the slope function, and then you will get the slope of the tangent, all right, or into the derivative function, right? First example is saying find the derivative of f of x equals x cubed from first principles. Explain in words what this derivative means. Okay, so what we're going to do here is we're going to use the limits to find the derivative function of f at x is equal to x cubed. So what we'll say is we can write our f at x right here, and we know that f at x is equal to x cubed, and therefore we know that f at x plus h should be equal to x plus h all cubed. Well, this literally means this binomial multiplied by itself 3 times. So that would require quite a lot of distribution. Alternatively, we can use binomial theorem if you wanted. So recall binomial theorem uses Pascal's triangle, which I'll quickly construct. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. And this is as far as I need to go for an expansion of the order 3. And what these are, these numbers here in Pascal's triangle represents the coefficients of each of the terms. Okay, so what I'll do right here is I know that x plus h all cubed is going to be equal to, I already know the coefficients, 1, 3, 3, and 1. Then I start off with my x cubes and I write x cubed, x squared, x, and x to the 0. And then I use my h's, because x plus h, I go to the second term, so h to the 0, h to the 1, h to the 2, h to the 3, and I add all the terms together. So cleaning this up, 1 times x cubed times h to the power of 0, x cubed, plus 3x squared h, plus 3xh squared, plus h cubed. So this right here is x plus h all cubed, which is my f at x plus h. So if I'm finding the derivative function from first principles, then I'm saying I need to find f prime at x is equal to the limit as h approaches 0 of f at x plus h minus f at x all over h. Again, limit as h approaches 0, and now f at x plus h I know is x plus h all cubed. And then I know that it is right here, all expanded, so I'll just go ahead and rewrite that. That is x cubed plus 3x squared h plus 3xh squared plus h cubed minus, and then f at x is simply x cubed all over h. Okay, you can see that or hopefully you can see rather, that the x cubes will cancel, and we will be left with the limit as h approaches 0, 3x squared h plus 3xh squared plus h cubed all over h. We can factor out an h. 3x squared plus 3xh plus h squared all over h. The h's can now cancel. This takes us out of the indeterminate quotient. And now I have this limit as h approaches 0 of 3x squared plus 3xh plus h squared. Direct substitution is now possible, and I get 3x squared. So what I can write here is I can write, therefore, f prime at x, or the derivative function, and the derivative function again is slope of the tangent as a function of x. So the slope of the tangent line, depending on the x value, is given by this function, 3x squared. So I will highlight this right here, and it says to explain in words what this derivative means. This means the slope of the tangent line as a function of x. So you input an x value, you'll get the slope of the tangent line. And this again is called the derivative. So now that we have the derivative function, the next example is saying, okay, well, this right here is our function, y is equal to x cubed. This is y is equal to x cubed. Alternatively, we could write that as f of x is equal to x cubed. Those are interchangeable. And it says determine the values of f prime at -2, f prime at 0, and f prime at 2, and interpret their meaning. So I know that f prime at x is going to be equal to 3x squared. We found that from first principles. So f prime at -2 is equal to 3. -2 squared, that's equal to 12. Literally, this means that the slope of the tangent at x is equal to -2 is 12. And let's see, I'm going to draw a tangent line there at x is equal to -2, and you'll see that it is in fact quite steep. So be right back. Okay, so I've drawn a tangent line at x is equal to 2. I'll just denote that. That's the point of intersection. That's x is equal to -2. And we can see that the slope of that right there is 12. So the slope of that tangent line is 12. Now what we're going to do is we're going to do the same thing at f prime at 0, and that's equal to 3, 0 all squared. So we know that that's 0. Well, that right there, anything with a slope of 0 is a flat line. So that is saying that at x is equal to 0, the slope of the tangent line should be flat. And that seems to make sense right here, because look at x is equal to 0, we have a flattening out of the cubic function. So I'll just kind of freehand draw my tangent here, and you can see that, yes, it is in fact a flat line at x is equal to 0. The slope is equal to 0 as well. Okay. Let's do our final one right here, which is f prime at 2. F prime at 2 is equal to 3, 2 all squared. That's equal to 12. All right, so it looks like the slope of the tangent line at f is equals, x equals -2, and the slope of the tangent line at x is equal to 2 will be equal. So I'm just going to take this tangent line right here. I'm going to copy and paste it and put it right at 2 as well. Okay, yeah, we can see that it is in fact parallel. So here is my x is equal to 2. And I can see that the slope of the tangent line there is also 12. All right, so the derivative function, again, allows me to calculate the slope of the tangent line given an x input. There's various ways that we can notate this. We can use Lagrangian notation, which is f prime at x or y prime. You see that quite often. Leibniz notation is dy dx, so the infinitesimal change in y over the infinitesimal change in x. So that really, really small change in y over change in x, that's also the derivative. Or you could say the derivative of f with respect to x, or the slope of the tangent of f as a function of x, right? And so we can see that right there. And then this one right here says, what it does is it allows us to evaluate the derivative at a specific a value. Okay, so we do our dy dx, and this vertical line says, okay, now evaluate that derivative at this x value. We typically do not see a lot of Newtonian notation, and you won't see it almost at all in this course. So the next example asks us to differentiate the function y is equal to 1 over x from first principles. Okay, so if that's the case, again, I'm going to use, I'll say y prime, I'm going to use y prime notation in this case, is the limit as h approaches 0 of f of x plus h, so that will be 1 over x plus h, minus f at x, 1 over x, and all of that is divided by h. Alternatively, we can say times 1 over h, because that's the same thing. Again, we move on and we see that what's required here is a common denominator. So I'll multiply this function right here by x over x. And I'll multiply the next function by x plus h. So I'll multiply this one by x plus h over x plus h just to get my common denominator. And what that will leave me with is x minus, and this one, remember I multiplied by x plus h, so x plus h all over x, and then x plus h is my common denominator. Recalling, I still have to multiply by 1 over h. Limit as h approaches 0. Well, hopefully you can see that the negative will distribute here. And so that'll give me x minus x, which is 0, but then it'll give me minus h, so minus h all over x, and then x plus h times 1 over h. We can see that the h's will in fact cancel, and then we are left with the limit as h approaches 0 of -1 over x, and then x plus h. Direct substitution is possible here. I'm not in the indeterminate quotient, so I can just go ahead and sub in h is equal to 0, and I get -1 over x squared. So that means that the derivative of the reciprocal function is -1 over x squared. So the slope of the tangent as a function of x is equal to -1 over x squared. And so I could input any x value provided it's not. I think one of the restrictions, we should probably write one of the restrictions here is x is equal to 0. X cannot equal to 0. Yeah, any other value of x, we can get the slope of the tangent. In this next example, we're going to determine the slope of the tangent at x is equal to 4 for f at x is equal to the square root of x by differentiating the function from first principles. So what I'm going to do here is, instead of just evaluating the slope of the tangent for only at x is equal to 4, I'm going to find the general derivative of this function, and then at the end I'll sub in x is equal to 4. So let's get started right away. We'll do f prime at x is equal to the limit as h approaches 0 of f at x plus h minus f at x all over h. Okay, and then I'm going to go the limit as h approaches 0, square root x plus h minus square root x all over h. Okay. And then I'll notice right here that I need to use the conjugate binomial, so I'll go x plus h plus square root x all over x plus h plus square root x. Creates a difference of squares in my numerator there. Okay, so I'll have x plus h minus x all over h bracket x plus h plus square root x. And I notice right here, x minus x, that subtracts to 0. Then I'll have h in the numerator, h in the denominator, that divides to 1. So I get the limit as h approaches 0 of 1 over the square root of x plus h plus square root x. Since I'm out of the indeterminate quotient, I can do direct substitution. 1 over square root x plus square root x is 1 over 2 square root x. So I'll just write a therefore statement here. Excuse me. F prime at x is equal to 1 over 2 square root x. And I'll notice right here that I have a restriction on the domain of my derivative function. Okay? Not a restriction on the domain of the original function, but the restriction on the domain of the derivative function is x has to be greater than 0. At this point now, I can actually find the derivative at 4. And so I'll go 1 over 2 square root 4, which is 1 over 2 times 2. And so that's 1 over 4. And so now I know that the slope of the tangent at x is equal to 4 for the square root function is 1 over 4. Now we're going to look at when a derivative actually exists. So function f is differentiable at a if f at a exists. Otherwise, the derivative does not exist. Below are the 3 most common ways for a derivative to fail to exist. So the first is what we call a cusp, and a cusp is a sudden change in direction. Okay, so I'll give you an example of that. So say we have a curve, comes down like this, and then all of a sudden it pops back up in this direction. Well, this is called a cusp. And no derivative exists at this single point right here. Alternatively, we can also have a corner. Okay, and a corner is like a cusp, except that you kind of have linear functions on either side. That's called a corner. This is called a cusp. And no derivative exists at these points right here. You cannot draw a tangent line, or you can't find the slope of the tangent at that point right there. The other thing is a vertical tangent. Now, a vertical tangent happens when you have a curve that is, for example, maybe like opening up right here, and then just at one point it goes vertical. We'll say right at this one instantaneous point, it's vertical. So if I try and draw a tangent line there, so I'm going to show you, I'm just going to input a tangent line. Okay, so here is my tangent line. And what we're going to do now is we're going to find the slope of that tangent line. So if I want to find the slope of the tangent line, I do y2 minus y1 all over x2 minus x1. But what you'll notice is, say we have 2 points on this line, which is vertical. You'll notice that even though the y values are different, the x values are the same. So for example, there's going to be an x value here, there's an x value here, and those x values are identical. So if we subtract identical x values, what we will have is we will have a 0 in the denominator. So if we have a 0 in the denominator, what we can say is the slope of the tangent is undefined for a vertical tangent, and the slope of a tangent, that's just another way of saying that f prime at a does not exist. Okay, so at this value right here, at this x value or this a value, whatever you want to call it, the derivative doesn't exist. Now we're going to look at discontinuities. So what I've drawn here is a curve with a hole at x is equal to 3. So notice that we can find the limit of the function as x approaches 3, what will not exist is the derivative. We can't find the slope of the tangent at a point that doesn't exist. Why might that be the case? Here is my definition of the derivative. So the derivative at 3 is equal to the limit as h approaches 0 of f at 3 plus h minus f at 3 all over h. Well, you might have recognized that we have a hole at 3, so that means this point is undefined, and I can't evaluate the derivative if one of the values within the definition is undefined. So I cannot find the derivative at x is equal to 3. All right, let's move on. Show algebraically that the function y is equal to absolute value of x is not differentiable at x is equal to 0. So why is it that this corner, there is no derivative at this corner? All right, so what I'm going to do is I'm going to write the general definition of the derivative. Okay, so remember that f prime at x is equal to the limit as h approaches 0 of f at x plus h minus f at x all over h. And now I'm just going to do a little bit of work on the side. Well, f at x is just defined as the absolute value of x, and f at x plus h is equal to absolute value of x plus h. Okay, so I'm going to rewrite this. F prime at x is equal to the limit as h approaches 0, and I'll say f at x plus h is the absolute value of x plus h minus the absolute value of x all over h. But I need to find the derivative at x is equal to 0. All right, so what I'll do is I'll do f prime at 0 is equal to the limit as h approaches 0 of 0 plus h minus absolute value of 0 all over h, and this simplifies to the following. Absolute value of h all over h. Okay, so to find this limit right here, I'm going to use one-sided limit. So I'm going to approach h from the left, and I'm going to approach h going towards 0 from the right. To do so, I'm going to draw a quick number line. That might help things a little bit. Okay, so here we go. Here's a 0. On the left side of the 0 are my negative numbers. On the right side of my 0 are positive numbers. So the limit as h approaches 0 from the left of the absolute value of h over h. Let's see what that is. So as I'm approaching 0 from the left, my numbers, my h values, are going to be negative. As h approaches 0 from the left, my h values will be negative. So the absolute value of a negative number right here is going to be a positive number. But then I'm dividing by the exact same number, h, except this one's not an absolute value, so this one will still be negative. So absolute value of negative h is just positive h divided by, and then this h will be negative because we're approaching 0 from the left. So positive over a negative is going to be negative 1 because it's the exact same number. Now, as I come from the right, the absolute value of h over h, so as I come from the right this way, my h value is going to be positive. The absolute value maintains its positivity. Divided by the exact same number, it's positive 1. And so what you might notice here is that this derivative, if I approach it from the left and if I approach it from the right, I obtain differing numbers. So the limit as h approaches 0 from the left of the absolute value of h over h does not equal the limit as h approaches 0 from the right. So therefore, the limit as h approaches 0 of this does not exist. And since this limit is just the derivative at 0, therefore the derivative at 0 does not exist. We can verify this answer looking at a graph of the absolute value function to the right. Well, as I approach 0 from the left, the slope of the tangent is negative 1. And as I approach 0 from the right, my slope of my tangent is 1. And as I get infinitely close to 0, the slope maintains its value of negative 1. And as I get infinitely close to 0 from the right, the slope maintains its value at 1, while the slope coming from the left does not equal the slope coming from the right, and therefore this slope doesn't exist at this point. Okay, so that's it for the derivative function. Thanks for watching.